Okay. Basically, let's try to remember what we did last time, and then we'll on, and then we'll continue. There's another technical thing I need to sort out. I hope it won't be long. Okay, so well, let's remember what happened last time. We did the following thing. We took a manifold inside C. Cn k plus 1, and we managed to cut it in such a way that m m prime does not intersect some slice. We'll be using those slices quite a bit. Let's denote them as a way. Now, does this terminology make any sense, or should I recall something? Should I recall everything? Гриша, значит, помним ли мы хотя бы что-нибудь из этого? Saman and Philip, does any of the letters on the board make any sense?
For me, it's fine. Yeah.
Philip. Well, there are several options. Okay, so let's see. So now Now we come back to the problem we started with. Namely, we want to show that the monoid BM the classifying space of M and K is the same as the classifying is the same the same as the space is somewhat equivalent to the space C and K plus 1. Well, more precisely, we don't want those groups just to be isomorphic. We want them. We want an isomorphism to be induced by a map. We constructed a map last time, and we want to show that this map, which we denoted sigma, induces an isomorphism of the homology. Sorry, of the homotopy groups. Well, let's. Well, let's prove that the induced map is surjective, and well, for injective, the argument is more or less the same, but we'll talk about that later. So we start with the map F, which goes from DQ to C and K plus 1. And by the way, let's recall that we assume that K is greater than 0. For K equals 0, things will be more complicated. We'll talk about it later. Such that F takes the boundary to the empty set. Okay, now we want to lift the map to BM to BM. Why? Well, because let's recall that for BM elements are collections of manifolds stacked together, one next to each other, along some of the coordinates, along the K plus first coordinate in our in Rn. Now, and the elements of Cn k plus 1 are just manifolds. The projection to the first k plus 1 coordinates is proper, but otherwise we don't know anything about them. So for now let's see what we have for every for every m inside Cn k plus 1, we are able to cut it once, well, at least once. But then we want to find a way to perform the cuts not just for one manifold, but for a family of them. And let's see, and this is where we need the classifying space and not just the monad itself. Okay, so for each t, there exists an interval. Such that m of t, which is how we denote f of t, will be deformable to a manifold m prime of t in the same way, where m prime of t has the property that it doesn't intersect some family of slices, namely those that correspond to J of t. Okay, now Now, my first claim is that the same is true for the same is true for all t prime inside some neighborhood of t in the Q disk, and well, let me call this neighborhood, I don't know, U. And well, it stands to reason that this correspondence M t prime goes to M prime t prime is continuous on U. Okay, now we want to do what? Which is a finite subcolor, and then we have the corresponding family of intervals. Well, we may assume that those intervals are disjoint. Otherwise, we shrink them a little or a lot, and the condition will be satisfied for slices that correspond to a smaller interval. If it's if it is for all slices that correspond to a larger interval. so we may assume that all intervals are disjoint. So as a result, we are able to deform not just a single manifold, but the whole family F. Now let's see. Let's see what this means. This means that for every ji, we perform the deformation on we deform the manifolds as described on the previous page on the corresponding neighborhood of some point in the disk. Okay, and then we once we've done this for J1, we do this for J2 and so on, and since the intervals are disjoint, what we do on the second step does not mess up what we've already done on the first step. Okay, so so we would deform the map F, and we get something. We get some well, some other map from the disk to C and K plus 1. Okay, so well, let's recall that for every t inside inside U ui, we have that empty, which is the same as f of t, is disjoint from the slice S of A, S of AI for some AI inside the interval Ji. Well, now we have we have a system of neighborhoods UI. We can choose a partition of unity. Which corresponds to the neighborhood. So well, we're almost done. I claim that this gives me a map from the Q disk to B. B, M, and K. Okay, well, what does this map do? Well, suppose I have suppose I have the T inside the Q. Such that at this point W1, W2, W3 are non-zero, and and the rest of them are zero. Now, now I want to define J of T. Now, what do I do? Are there any suggestions? Well, before I define J of T, let me state the obvious. Well, if I have three of the W's non-zero, T belongs to what? To U1 intersected U2 intersected U3. Okay, so in fact, MT does not intersect three slices, which are all destroyed. Grisha, does this make any sense?
Yes, I think so.
Okay. Now, well, those A1, A2, A3 are all different, but well, they're not necessarily ordered 1, 2, 3, but they are ordered in some way or another. So assume I don't know, A2 is less than A1 is less than A3. Okay, so now we have a way to cut M into 4 pieces. And I also have some family of W's. So let's see where I take G of t. So G of t should be an element of V M N chi, and and now I've run into a problem. I should have something like I should have here I should have an element of MP delta P, while instead I get another simplex, which is not particularly good. Okay, so let's see where I went wrong. Are there any suggestions? Well, in this case, I have 4 manifolds, but only 3 non-zero weights, meaning only 3 non-zero W's, and this gives me what? This gives me an element of which simplex? Philip, if I have 3 non-zero real numbers which add up to 1, this is an element of the simplex of which dimension? For example, if I take 1/3, 1/3, 1/3, this is the center of which standard simplex? Okay. Well, Philip decided not to answer the question. Okay, Simon, what do you think?
I mean, your example must be two-dimensional. I mean, generally, it can be thought as a point in unordered configurations of an interval, right?
Yes, but this yes, but this is not directly related to. Anyway, so yes, we have an element of the simplex of the standard simplex of dimension 2, and we only have well, we only have a two-dimensional simplex, but I have 4 manifolds. So what should I do? Are there any suggestions? Well, the simplex is two-dimensional. There's nothing else we can do with it. So what about the manifolds? Гриша, что нам делать? У нас многообразие получилось 3, даже 4, значит, симплекс получился двумерным. Нам хочется, чтобы значит, одного было столько, сколько другого. Вот, ну давайте посмотрим. Well, let's have a look. The picture at the bottom of the page is the picture in which coordinate? Значит, то, что здесь нарисовано внизу, происходит по какой координате? Saman, this picture in this picture, the horizontal axis is which coordinate?
In this picture, it must be, I mean, on E2, right? I'm not sure.
We have multiplication in CNK plus 1, and this multiplication is consists in putting things next to other things, but in some coordinate. Grisha, do you remember which coordinate this is?
No, I'm afraid not.
Okay, in MK plus 1 and in C N, sorry. Let's try to remember the definition of C and K. M and K is very similar. So C and K, what is this? It's a set of all properly embedded manifolds M inside Rn, such that M in fact lives in R chi cross 0, 1 to n minus chi. And we stack them together. In the k+1th coordinate. Basically, if we want to remain inside C and K, we need to compress those manifolds, and then we stack them together. In M and K, we allow the k+1 coordinate to be inside any finite interval 0 something. So we stack together in x k+1. So here we have x k+1. But M or MT is in fact an element of C and k+1. So in particular, M1 and M2 can be thought of as elements of M and K, but not M0 and M3. So we cross them out. They do not necessarily belong to or even they do not necessarily belong to M and K. Well, for M3, the K plus first coordinate may be very, very large, and for M0 it may be very, very small. Too large and too small, respectively. Okay, so we just drop the first and the last manifolds and forget about them. And then we take W1, W2, W3. And then we take the equivalence class and we get an element of M2 cross delta 2. Okay, Grisha, Saman, does this make any sense?
Yes.
Yes.
Okay, so so here we constructed the map from map G from the Q disk to the classifying space. Well, if I take first, well, G first and then sigma, I get a map which is homotopic to F, to the map F we started with. Well, let's try to remember what all those maps and moreover relative relative to the boundary. Well, to see this, let's try to remember what those maps do. Well, F well, F takes a manifold and produces some way to cut it along several slices and a system of weights. No. This is what G does. F just produces a manifold. What does G do? We cut this manifold along the slices, and then what does sigma do? Does anyone remember what sigma does? Well, sigma sigma takes a manifold, or more precisely, a collection of manifolds, and then a collection of manifolds plus numbers stacks them together. The manifolds, and then extends or rescales the whole thing in the k plus first coordinate, depending on how close the weights are to w naught equal 0 or wp equals 0. So the first and last components of this contraption, meaning the manifolds stacked next to each other along xk plus 1, may escape to infinity. Simon, Grisha, and Philip, does this agree with what I said last time?
Yes,
I guess
think
yes.
so.
Okay, so let's compare the left-hand side with the right-hand side. So on the left, we just have a manifold, and on the right we have no, on the right we just have a manifold, and on the left we have the same manifold with the first and last components dropped. They're not good enough, and one of the middle components pushed to plus or minus infinity depending on the weights. Well, the pictures are similar but not identical. So what do we do? Well, we basically use the same trick which we use to define sigma. We push the extra components that we lose along the way to infinity. To minus infinity, respectively plus infinity. Okay. Now the okay. Are there any questions? This was the subjective part, and well, the injective part is essentially essentially the same. So let's okay, let's go through the proof for let's go through the proof of surjectivity again and see if we see if there are parts that need some more explanation. Grisha, do you understand why we dropped why we had to drop M0 and M3 in this picture?
Yes, I think so. Yes.
Okay. Well, let's see what happens near near the boundary. This may be. Or actually before this, let's take a t inside the boundary. The boundary goes to the empty set. Let's see what let's see what happens when we when we have a point t on the boundary on the sphere. Well, f of t will be just the empty set. Well, the empty set is empty. So it is so basically any slice would sorry. We may assume that one of the neighborhoods is a neighborhood of the boundary, and the corresponding interval can be chosen arbitrarily. Well, let's assume that it contains 0. and let's take S of 0 as the disjoint slice. Then let's also assume that none of the remaining UI intersects the boundary. Then the behavior of what did we construct? The G on the boundary is identical to the behavior of F, meaning G takes the boundary to the empty set. Okay, and so on. Are there any questions, comments, criticism? Okay, in this case, I suggest we have a break, and then we let's skip the argument which shows that the map is the map of the homot of the groups is injective. Well, because it's very similar. And let's start talking about the other case, the harder case. What do you think? And in the meantime, I'll try to I'll try to get the other program working, and we'll see whether or not it works. Hard case k equals 0. And well, let's recall that a few weeks ago, and by the way, the dimension D will be 2. And I'll now recall what M actually is. Well, M is the direct limit of Mn. And what is Mn? Well, it's the space of surfaces in well, A is a real number, non-negative. A is a surface in R cross not R cross. Now we want to pass to compact manifolds at some point. So S is a surface inside 0 A cross Rn minus 1, such that the boundary is two circles and those live in the hyperplanes. The first coordinate is 0 and the first coordinate is A. Well, the second condition is a bit technical. We'll later see where it comes in. I want the bottom half of S to be standard. What is the bottom half? Well, the bottom half is well, shall we say -1, 0. Well, not quite R. 0, 1, and -2. So the bottom half of S is the standard cylinder is the same as the bottom half of the standard cylinder. And by the way, let me put okay, let me put -1, 1 here. Not just R. -1, 1, -1, 1, 2, and -1. And let me also put -1, -1 here. Okay, well, what's the picture? Well, the picture is something like this. Okay, and there is one more condition. We require that the behavior near the boundary should be standard, meaning the same as the same as for the standard cylinder. Well, this is technical. We want to be able to glue those surfaces together. That's why we make this requirement. Well, the degenerate case A equals 0 is allowed, in which case we have a circle instead of the surface, and this the circle will be the identity of the monoid. Okay, does this picture and the explanation make any sense? Now, what do we want to prove about this monoid? Well, first of all, there is a map sigma from DM to C infinity 1, which is constructed just as the map sigma from the previous proof. And we want to show that this map is an equivalence. Well, there's one difference between BM infinity and BM and K, and well, this difference is we have in one case we have the disjoint union as our operation, and in the other case the operation is connected sum. But otherwise, the construction of sigma works just the same. Well, if you remember, this is one of the steps we used in the proof of the theorem. Okay. Well, let's first go through the general strategy. Oh, and by the way, what is C infinity 1? Well, this is easy. It's just the direct limit of Cn1. So we will construct maps such that both maps raw and tau are equivalences or weak equivalences. So the word weak is written in weak yellow. Well, just to stress the point. And the diagram homological commutes. Okay, well, let's try to implement the first few steps of this strategy. Or more precisely, the definition. There's well, the definition is well, straightforward enough. Okay, so the well, the space C infinity 1s is the space of couples or actually tuples. Such that well, the second group of numbers add up to 1. Now, the second condition is the same as the second condition. By the way, before I talk about the second condition, what is S? Well, S is a surface. Well, what does it mean? Well, this means S is properly embedded in R infinity, and the first coordinate may vary from minus infinity to infinity, and the remaining coordinates are bounded. Well, so S is inside R cross, and let me put here minus 1, 1. Minus 1, 1, infinity minus 1. Okay, well, the second condition says that the bottom half of S well, it's not really a half, but anyway. What is the bottom half? Well, it's S intersected with R cross minus 1, 0 cross minus 1, 1 to infinity minus 2. Is standard. What does standard mean? Well, this means it's the same for, as it's the same as for standard cylinder, which is R cross R cross S1 inside R cross R2 inside R cross R2 cross R infinity minus 3. Well, the picture is just the same as this one, except Now the surfaces can stretch to the left and to the right indefinitely. Okay, so let's call this okay. Condition 1, condition 2, condition 3. Condition 4. S intersected with S of A. I will shortly explain what this means. Is the same as for the standard cylinder. Okay, well, what is S of A? Well, first of all, what is A? What is sorry? What is AI? Well, AI is one of the numbers which are part of the data, just real numbers. Okay, what is S of AI? Well, this is the same as the hyperplane x1 equal AI in R infinity, where x1 is the first coordinate. Well, basically in this picture, x1 is the horizontal coordinate. It is the coordinate along which we glue the surfaces in this monoid. But here, the behavior of the surfaces is slightly different. They may extend to plus infinity or minus infinity along this coordinate. So we don't really know how to glue them. But anyway, we'll come back to this in a minute. No. And lastly, we require that the part of S between each two consecutive slices should be connected. So basically, the picture is very similar to this one, but slightly different. Let me draw it again. No, well, this is it's not very good. Let me try again. So we have well, we have something to the left of A0, something to the right of A2. We don't know what this something is, and all we require is that the part between A0, A2, sorry, A0, A1, and A1, A2 should be connected, and the behavior around each circle should be the same as for the standard cylinder, and this is basically it. So there could be there may be other components floating around, provided they are to the left of A0 or to the right of A1. And also provided they do not mess up this condition, which says something about the bottom half. Well, there is another another thing to keep in mind, which I will shortly state. But let's first have a look at this definition, and there's one thing that's pretty straightforward. This space, on the one hand, resembles the classifying space of something, and on the other hand, it resembles C infinity. So it's a sort of a hybrid between Dm infinity and C infinity 1. And we need to prove that this hybrid is homotopy equivalent to both. Now there's one extra convention which is similar to what we have seen already. If one of the weights is 0, the corresponding numbers AI are deleted from the data. It is possible to state this rigorously, but I'd rather not to, because it will make things worse, not better. Well, what we really want is to take the product of to take the disjoint union of the products of the synthesis with some polyhedra, and then take some equivalence relation on this space. Now, do we want to dig into the gory details? Well, it's more or less. I think it's more or less clear what this phrase means. If it isn't, please let me know. Otherwise, let's just go on. Okay, so we constructed a map from no. We constructed some space. C infinity 1. Basically, the map. No, what is it? The map tau from C infinity 1. No, C infinity 1s. Just forgets all all the pieces of the data except S, and just keeps S, and we arrive in C infinity 1. No surprises there. What about the other one? Let's see. Suppose we want. Suppose we have. Suppose we have. We have a surface like this one. And we want to get a surface like this one. What do we do? And some numbers. Elements of Bm infinity are tuples of elements of M infinity plus some numbers. Well, the numbers we have them. W naught, etc., WP. And so, for example, in this example, we have A naught, A2, sorry, A naught, A1, A2, and we also have three numbers. Which are inside 0, 1, and which add up to 1. Okay, so how do we construct an element of Bm infinity starting from this data? Are there any suggestions? Гриша, как получить отсюда элемент классифицирующего пространства? Вот пусть у меня есть такая поверхность, вот как нарисована, я хочу какой-то элемент, значит, Bn, вот буквально такая, как нарисована. Вот я хочу какой-то элемент Bn бесконечности.
Сейчас, а почему нельзя просто поверхность смотреть как многообразие, которое представляет какой-то симплекс или четкую фигуру?
Значит, нам нужно что? Нам нужен какой-то набор поверхностей, значит, но уже, значит, таких компактных с границей, которые живут значит, вот где-то здесь. И какой-то набор чисел. Значит, на набор чисел у нас есть, вот у нас есть вот эти вот числа W, мы с ним уже ничего не сделали. Значит, откуда нам взять поверхность в нужном количестве? Вот, значит, в данном случае у нас, значит, у нас опять W1, we again have in this example an element of the two-dimensional simplex given by W0, W1, W2. So we have a two-dimensional simplex, and we need to get two surfaces. Well, just by looking at this picture, it's pretty clear how to get two surfaces with boundary. We throw away everything which is to the left of a node and everything which is to the right of A2. And then we cut along A1 and we get two surfaces. Grisha, does this make any sense?
Yes.
So the map road, what does it do? It forgets everything. The part to the left of a node. And the part to the right of AP. And we cut along the remaining slices SA1, SA2, SA3, and so on. So we set a row of S, comma, A node, AP, W node, WP to B. S1 and so on, SP, or more precisely the equivalence class in the classifying space. Where SI is between the slice at I, sorry, AI minus 1 and S of AI. So for example, well, here we have S1 and here we have S2 and this is it. Okay, so now we have constructed the two maps. The one, well, the first one is completely straightforward, and the second one just consists in chopping off the part to to the left of A0 and to the right of A2 or AB in the general case. Okay, now we want, what did we do? So we constructed some space, we constructed maps. Now, proving that those are homological equivalents is tricky. But what about proving that rho sigma, rho composed with sigma, is homotopic to tau? Well, let's see what all the maps do. Well, tau just forgets the extra data. What is the extra data? It forgets the AIs and the WIs. Okay, so this is easy. Now, what does sigma rho do? Well, no. Is it sigma rho? No, it's rho sigma. Sorry. So we first apply rho, and then apply sigma. Okay, so when we look at the right-hand side, we just end up with the surface without any further decorations. What happens when we apply the left-hand side? Okay. Again, let's consider this this particular example. So we have a surface plus some extra numbers such that. Okay, and when we apply tau, we basically forget about the numbers. Now, what do we get when we apply first rho and then sigma? Well, I think one should be more careful with the definition of sigma Well, let's remember what this map does. When one of the weights tends to zero, we we push the corresponding surfaces to infinity. But let's think a little. I think we need to do the same. I think we need to do okay. There's one thing which didn't happen in the previous case. Basically, when we use the direct sum, sorry, the disjoint sum as our operation, we don't need to do anything apart from stacking all the manifolds together. But in this case, I think we need to basically add the copies of the standard cylinder. So let me of the standard cylinder to the left and to the right of the resulting manifolds. Well, not exactly copies, but okay. I will try to draw the result here. As I have some surface S1 and some other surfaces too. And this is what I get when I stack together elements of M infinity. But then I get a compact surface with boundary, which is not what I want. Well, not quite what I want. and I extend this by attaching copies of the standard cylinder on the left and on the right. Grisha, Simon, does this make any sense?
Yeah.
Yes, it does.
Okay, well, let's now come back to this homotopy. Okay, let me. We're running out of time, so let me explain what this homotopy does in this particular example. So in this particular example, we have we start with S1, S2, something 1, and something 2. And so this is what we start with, and the right-hand side is the same, except we lose all the numbers. What is the left-hand side? Well, the left-hand side is 1 connected some with S2, and then instead of something 1 and something 2, we attach parts of the standard cylinder. Well, how can one connect the picture on the left with the picture on the right? Well, by pushing both something 1 and something 2 to plus or minus or plus infinity by stretching. By stretching along the first coordinate. Okay, this is a description of sorts for the homotopy between sigma and rho. Sorry, no, between tau and rho composed with sigma. Does this description make any sense? Saman, does it or does not?
Yes, it does. It's fine.
Гриша, значит, имеет ли происходящее хоть какой-нибудь смысл?
Вроде да.
Okay, well, I suggest we stop here, and basically next time we will try to prove that well, at least one of the maps tau and sigma induces an isomorphism of the homotopy groups, and hence is a homotopy equivalence. And then we'll see how it goes. If we realize we're tired of the technical details, the week after next we'll talk about something else. For example, Saman, are you ready to speak about? I've forgotten the topic, but.
Yes, I'm ready. The topic, I don't know the name of the theorem. I mean, I can't pronounce it.